Welcome. Let me remind you that in the last class we had embarked upon trying to understand the nature of the space-time in cosmology, and I had started off by first briefly recapitulating the nature of space-time without the effect of gravity, and the space-time properties can be characterized by this quantity ds square, which we referred to as the line element or the interval, and this formula tells us how to calculate the interval between two events. Events can be represented on a space-time diagram like this. So each event has a corresponding position and time when it occurred. So you can represent events on a space-time diagram, and if A and B are two events, you can calculate the interval. If these two events correspond to the same point, same coordinate at different times, so imagine a person sitting at one place, then you will get a positive value for the interval, and these two events are said to be time-like. What was very important, I had pointed out, is if you look at the propagation of light, light will propagate along a curve. So if this is the curve along which light is propagating, we are considering only the x-axis. Let us assume that the y and z direction remain fixed. Then delta x is equal to c delta t for light. So delta x is equal to c delta t, and if you put that in here and calculate the interval, you will find that the interval turns out to be 0. So for two events which are along the trajectory of a photon, the interval is 0. The expression for the interval or the line element can also be written like this, where we have written the spatial distance separation in spherical polar coordinates. Now in Einstein's theory of relativity, the gravitational field manifests itself as the curvature of space-time, and here in cosmology, the cosmological space-time has the property that it has to be the cosmological space-time has the property that the space has to be homogeneous and isotropic. So the line element or the metric allows us to calculate distances between points. The line element, the cosmological line element, where the space is homogeneous and isotropic, has been written over here. This is called the Friedmann-Robertson-Walker metric. It was independently written down by Friedmann, Robertson and Walker, and possibly by other scientists also at roughly the same time. And I was trying to explain to you what the various terms in this mean. Now time here is the cosmic time. C is the speed of light, A is the scale factor which is already familiar to us. It quantifies the expansion of the universe. The x is the co-moving radius. We are working in spherical polar coordinates, so x is the co-moving radius. We are working in co-moving coordinates because you can see that there is a scale factor over here. So x is the co-moving radius, and you have this extra factor. If this factor k were 0, if the factor k were 0, then this line element would be exactly the same as this line element, except for a scale factor squared over here. But we have this extra term k into x square by L square also appearing, and k, this presence of this non-zero k indicates that there is spatial curvature. My space is curved. My space time is going to be curved because of this scale factor here, okay, but the presence of this k indicates that my space is curved, and L is the radius of curvature in comoving. So, this is the comoving radius of curvature of that space. So, k equal to 0, if I have k equal to 0, this is spatially flat. And here the line element is ds square is equal to c square dt square minus a square So, this is how you calculate length in the usual flat space, polar coordinates, and the lengths, these are comoving lengths, get multiplied by a square, length squared get multiplied by a square because the universe is expanding, and the line element is just given by this. So, I would think that this should be quite comprehensible to all of you. Comprehensible to all of you, you should be able to understand this quite easily. Okay. Now, the question is what happens when there is a k and L which are non-zero. L, there is no the radius of curvature, there is no radius of curvature, it is infinite in this when k is 0. Okay. Now, I have told you that we had introduced when we solved the Einstein, when we solved the equation for the expansion of the universe, we had encountered a constant of integration 2e, and this appeared in my equation for the Hubble parameter in this combination, if you remember, and this we had replaced, we had parametrized this by a fictitious density omega k, whose contribution falls as a square as the universe expands, and the contribution from this fictitious thing which I had told you corresponds to curvature was quantified using omega k naught. So, if you now take, you see in Einstein's theory of gravity, you do not use Newton's the laws of gravity are modified, they are given by Einstein equation, and if you write down these equations you have some relations between the metric. So, they relate the curvature of space time to the matter which produces gravity, and they give you relations between the scale factor, they give you relations between the scale factor and k and L. So, these things are related to the matter density, and these equations turn out to be exactly the same equations that we have derived from Newtonian considerations, with the modification that rho gets replaced by rho plus 3p by c square. Okay, they turn out to be exactly the same. So, if you now work out Einstein's equations, in those equations you will have k and L appearing. If you relate those, if you identify that equation with the equation that we have derived, you will find that you can relate omega curvature or 2e by a square to this k and L which I have introduced here. It follows from Einstein equation, and the identification is, let me just write it down, I will not work it out here. The identification is that omega curvature naught is equal to minus k c square Okay, so let me remind you again, this is something that we have already encountered. We have introduced this to essentially parameterize the contribution from this constant of integration. This is the value of k and L are related to that constant of integration which we had encountered. That relation comes if you look at the Einstein equation. I will not do the derivation here, let me just place it before you. That relation comes out to be this. Okay. So you are led to this relation if you really work through the Einstein equation. So it follows that if the constant of integration is 0, then so if E or omega k naught equal to 0, it implies that k equal to 0. The space is spatially flat. The space is this part of the line element refers to the space. It is spatially flat. It is the usual flat space. Okay. Now the question is, what happens when this constant of integration is not 0? What is the curvature? What is the value of k? So it's quite obvious that if omega curvature naught, if the constant of integration is positive, these are the models. If I have only matter and this constant of integration, these are the models that will keep on expanding forever. This is the critical model. If I have omega curvature naught greater than 0, then k is equal to -1, k is -1, and if omega curvature is less than 0, then k is 1, and this is called, so the previous one was spatially flat, this k equal to 0 is spatially flat. This has a positive, this is a space of positive, constant positive curvature. And this is a space of negative constant curvature, constant negative curvature. Okay, and the radius of curvature L is this is the radius of curvature, co-moving radius of curvature. Co-moving, and the curvature is 1 by the radius of curvature squared. So the so if you want the physical radius of curvature, then it is a into L, and the curvature, which is denoted by r, is of the order of, is actually equal to 1 by a square L squared, the curvature of space, not of space time, of space. Okay, so this is a brief gist of the properties of this space time. Let me now explain to you, try to explain to you what we mean by a space of constant, let us say positive curvature. Okay, so let us look at this case a little closer. Take a closer look at this case where k is equal to +1. So the situation where k is equal to +1, and we shall only deal with the spatial part of this, which allows us to calculate the co-moving distance. So let us try to interpret what this space looks like. So the space, the line, the distance between 2 points in that space is given by dl square is equal to dx square 1 minus x square by L square plus x square d theta square plus sine square theta d phi square. So, let us try to get a picture of what this space looks like. What does this space look like? For this, it is convenient to introduce new coordinates x is equal to L sine, sorry, not x, chi or sorry, x is equal to sine chi by L. So, this is chi by L, x is equal to L sine chi by L. Before we before we embark upon this, let me point out that the range of x, you see this space, the radius x is the distance from the origin, x is the radius, and in the usual flat space the radius can go from 0 to infinity, there is no restriction. You see in the usual flat space, look at this, there is no restriction on the radius, it can go from 0 to infinity. But in this space there is a limit, the value of x cannot exceed L. So, x is equal to, in the range, x has to vary in the range beyond which this thing will become negative. Obviously distances cannot be negative. This allows us to calculate distances between different points, and that obviously the square of the distance, that obviously cannot be negative. So, L has to be in the range 0 to L, x has to be in the range 0 to L, or equivalently chi has to be in the range 0 to pi. The variable chi that we have introduced has to be in the range 0 to chi. Okay. X is the distance from the origin and x is restricted to 0 to L. So, you cannot go a distance further than L away from the origin, it is a different kind of space altogether from the usual space that we are normally used to. Yes, there is a question.
So, why can't x vary from minus L to L?
Well, x is a distance, right, it is a radial distance, how can the radial distance be minus? So, the x is a radial distance from the origin, we are in the polar coordinate system, so x goes from 0 to L, not from minus L to L. Okay, fine. So, let us now replace the variable x with chi. So, to do that, all that you have to do is you have to replace it here, and this becomes sine square, sorry, let me remove this chi by L here. X is chi, let us make chi dimensionless, okay, sorry, otherwise I will have to put extra factors of pi L. So, L x is equal to L sine chi, and the range of chi is 0 to pi. Okay. So, with this term it becomes d square chi, d chi square, because the numerator becomes L square cos square chi d chi, d square chi, the denominator is also cos square. So, the line element over here, if I write it in terms of this variable chi, it takes on the form dl square is equal to L square d chi square plus chi square, no, sorry, it will not be plus, sine square chi d theta square plus sine square theta d phi square. This is how we calculate length. All that I have done is I have just changed variables and gone from x to chi, where chi is sine, well, x is sine L into sine chi.
So, where did you get it that x is equals to L sine chi?
I am making a substitution, that is all. I am given this formula for calculating distance between points. I am replacing x with a new variable chi. I can always change my coordinates, right? So, that is all I am doing. for my convenience, and the convenience will be clear just now. So you see the way you calculate distance in this coordinate system, it's d chi square sine square chi d theta square plus sine square theta d phi square. Okay. So this is like a polar spherical polar coordinate system, except that you have this extra coordinate chi appearing. Okay, so this is the thing that we will try to interpret. The interpretation of this is quite easy. To interpret this, let us fix the value of chi. Let us look at some fixed value of chi. Okay, so if I look at a fixed value of chi, then if I look at a fixed value of chi, let me write this down here. If I look at a fixed value of chi, then the distance between 2 points, the chi doesn't change, it becomes L square sine square chi d square theta plus sine square theta d phi square. So I am looking at a fixed value of chi. Let me now look at a fixed value of theta. Phi is the only variable. So for a fixed value of theta, phi is the only variable. So now you see that you can think of this as being it's basically a circle. If phi is the only variable, we have a circle, right? Phi is the only variable, so we have a circle, and the distance between 2 points on that circle is d phi into L sine chi sine theta. Let us just ignore this part. So this is a circle, and that radius of that circle just increases with theta. It is 0 when theta is equal to 0, it is 0 when theta is equal to pi, and the radius of the circle, this is the radius of this whole thing is the radius of the circle. This we will focus only on this part. So the radius of the circle keeps on increasing with theta. So let me draw it here. This you can see is a surface in 2 dimensions. It's a 2-dimensional surface, 2D surface. It's basically a 2D sphere. Right, nothing more than that. The radius of the sphere is L square sine square chi. Sorry, the radius is L into sine chi. And let me draw it. So this is my x, y, z, and this is my sphere. This is the angle theta. For a fixed theta, this is my angle phi varies in this direction in the xy plane. This is my circle. So essentially what this tells us, only this part, what it tells us is that I can think of a circle as a sphere as a collection of circles. The radius of the circle is 0 at the north pole. The radius of the circle is also 0 at the south pole, where theta is 0 and pi respectively. The radius of the circle increases as I come near the equator, and it is the maximum at the equator, and again it becomes 0 at the 2 poles. Okay, so a 2D sphere can be thought as a collection of 1D spheres. A circle is a 1D sphere. Okay, circle, basically circle, and they are stacked up like this. Okay, I hope it is clear. So a 2-dimensional sphere, this is a 2-dimensional sphere, the surface is 2-dimensional, can be thought of as a collection of 1-dimensional spheres at different values of theta, and the radius of the sphere varies from 0 to the maximum value which is given here, that is the maximum value, into this, that is the maximum value, and then again it goes to 0 at the other pole. Okay, so this is a 2D sphere. Now look at this. This you can see is a collection again. So this is a 1D sphere, 1-dimensional sphere, collection of which gives me a 2-dimensional sphere. This is a collection of 2-dimensional spheres along the variable chi. The radius of the sphere is L sine chi. The range of chi is 0 to pi. this is chi. So for chi equal to 0, I have a sphere of radius 0, okay, it is a point, and then for chi equal to pi the sphere has the maximum size, and again it becomes 0 here. So you see this is a collection of 2D spheres, this is what is called, whose radius keeps on varying as I go towards the equator is at chi equal to pi by 2, and then again it decreases as I go to chi equal to pi. This is what is called a 3D sphere, it is a 3-dimensional volume which is a sphere. It's a generalization of a 2-dimensional sphere, it's 3-dimensional, it's a sphere, okay, and this is a collection of, I can think of it as a collection of 2D spheres which have been all stacked together, okay, and I can generalize this, I can have a 4-dimensional sphere, 5-dimensional sphere, 6-dimensional sphere, all I will have to do is add more variables, zeta, sine squared zeta, etc. Okay. So the radius of this 3-dimensional sphere is L, just like the radius of a 2-dimensional sphere here is L square, forget about this, is L, right. This represents a 2D sphere with this equal to 1, this represents a 3-dimensional sphere with radius L, okay. So k equal to plus 1 is this space is essentially a 3D sphere, so 3-dimensional sphere. The surface of the earth, for example, is a 2-dimensional sphere, okay, this is a 3-dimensional sphere, and the way you can imagine this is that there is a space, in that space, so a 2-dimensional sphere, for example, on the surface of the earth, if I go forward on the surface of the earth, after some time I will circumnavigate the earth and come back from the back. If I go this way, I will after some time go around the entire earth and come back from this side. Similarly, in a 3-dimensional sphere, if I go up, given adequate time, I will go around the entire sphere and come back from the bottom. It is a 3-dimensional sphere, it is a bound, it is a finite volume, it has no boundaries though, okay, there are no boundaries, but the volume is finite, just like the surface of the earth, it is a finite area, but the boundary, there are no boundaries, okay. So this is what we have when k is equal to plus 1. It is a space of constant curvature, just like a 2-dimensional sphere, and we have some idea now what it looks like. Similarly, k equal to minus 1 is a space of negative curvature, okay, k equal to plus 1 is a space of positive curvature, and k equal to constant positive curvature, k equal to minus 1 is a space of constant negative curvature, okay, and it is convenient to rewrite this cosmological metric, sorry, not this, it is convenient it is convenient to rewrite the cosmological metric in the following form. Let me just write it down for you. So it is convenient to rewrite the cosmological metric in the following form. We will write it as ds square is equal to c square dt square minus a square and then we have dr square plus s of r d theta square plus sine square theta d phi square. Okay, so I have written the same line element which I had written down right at the start of today's class, it is exactly the same line element where we have now introduced. So this is the line element I was talking about. I have just written it in terms of new variable r. R also is a comoving distance. I have written it like this, where remember that we had x square here, we now have a function of r over here. This function of r, s of r, is equal to r if k is equal to 0. That is the familiar s of r square, familiar flat space. Okay, d square r plus r square d theta square plus sine square theta, etc. Okay, now this function s of r is L sine r by L if k equal to plus 1. We just saw this, except that we used a variable chi which was dimensionless, and now we will use a variable r by L. So the range of r is from 0 all the way to pi into L. Okay, and this is if k equal to plus 1, positive curvature. If k is equal to minus 1, then we will represent this as sine hyperbolic. That function s becomes sine hyperbolic. You have to do exactly the same thing as we did for k equal to plus 1. You will then find that the function s is of the form sine hyperbolic L into r by L if k is equal to minus 1, and there is no restriction for both these cases. R can take any value more than 0. Okay, the spaces are infinite, these two, in these two cases, negative curvature and no curvature, but if it is positively curved, then the space is finite. Okay, so this is the general cosmological metric, that line element that we shall be using. So the cosmological space time in general can be represented like this. The form of this function s of r depends on the value of the omega curvature, not how much curvature, basically is parameterized by that. Okay, so this is the form of the cosmological space time. Now let us use this to calculate certain interesting things. Right, after all, the space time, the form of the space time is important only if it is useful. So the question is, what use is this in cosmology? We have already seen that we can determine the evolution of the, in principle one would take this and put it in Einstein's equation, determine the equations governing A. But we have already done this from Newtonian considerations, just extending it a little bit. Okay, so now we will see what other utility this thing has. And the place where you cannot do without relativity is essentially if you look at the propagation of light. Propagation of massive particles can be very well studied without the aid of relativity in most situations if they move slowly. But things that move at the speed of light you cannot study without relativity, because the Galilean laws of transformation do not hold. Okay, so let us look at the propagation of light in this space time. So the situation that we are going to consider is as follows. We have an observer sitting over here and there is a galaxy over here, and the observer receives some light coming from the galaxy. That's what we normally have in astrophysics. Right, so if you have observations, an observer is receiving light coming from a galaxy, and let us say that the galaxy is at a comoving distance r with respect to the observer. Now, and let us say that the light was emitted here at a time t emitted, and it was received here at a time T observed. This is T observed, okay, not T present, not necessarily T present. TO and TE. So we would like to see the propagation, study the propagation of this light. I have already told you that the most important thing about this interval is that it is 0 along the trajectory of a photon, along the trajectory of light. So the propagation of light from this galaxy to this observer is along a trajectory which satisfies C dt is equal to AT dr. The light, we are assuming, propagates entirely along the radial direction. So these terms are not going to be there, d theta and d phi. And this is nothing very special, because we can always choose the coordinate system so that one of the points is observer is at the origin and the galaxy is somewhere else. Okay, so this is the situation that we are dealing with. Light propagates along a curve which satisfies this. So we would like to now, to determine the trajectory, you have to now integrate from T emitted to T observed, right. So what we can say from this is that C, the integral T emitted, and there will be a minus sign here, because as time increases the distance r decreases. Well, you could have taken a positive sign if the light were going outwards. Okay, so we have to integrate this, and we have to integrate it from T emitted to T observed, and we have to integrate dt by AT, and we have to integrate the right hand side from r to 0. This will give us r. Now light, we know, is a wave. Okay, so there is a wave actually which is coming from here, and there is a wave which is being received over here. We would like to now calculate the redshift of the light. Does the frequency, we like to address the question, does the frequency of the light change when it propagates from the galaxy to the observer? That is the question that we would like to address. So we know that light is a wave, so let us just draw a wave which is emitted. So the wave which is emitted at the emitter will look something like this. This is T emitted, and this is the oscillation that is being transmitted, that is being emitted. So this is T emitted, this is the amplitude of the light. Let us call this some capital A, amplitude of the wave that is being transmitted. And let us say that this is the time instant Te when one crest is emitted. This is the time instant Te plus delta Te when the next crest was emitted. So there are two crests in this wave which are emitted at a time interval of delta Te, and we know that the frequency of the light nu emitted is equal to 1 by delta Te. This is also equal to C by lambda emitted. Okay, so basically delta Te is proportional to lambda emitted. Similarly, this is the emitter, what the emitter emits. The observer will also receive something which is exactly identical, except that maybe the time period will be different. So the observer will receive the first crest at a time T observed, and he will receive the second crest at the time T observed plus delta T observed, and the observed frequency, or 1 by delta T observed, is equal to C by lambda observed. which is okay. Now so there is one crest which is emitted at t emitted and received here at t observed, and that will follow this trajectory, it will travel at the speed of light. So we have written down the equation that governs it. Let us now write down the equation that governs the propagation of the second crest. The second crest will follow exactly, you see in the comoving coordinate system the galaxy remains at the fixed coordinate, the observer also remains at the fixed coordinate. So this right hand side will not change, it is basically just the right hand side is the comoving separation from the galaxy to the observer, which remains fixed. Okay, the limits of the right hand side integral, left hand side integral will be different. So for the next crest, for this crest and this one, the limits of the integral will be t emitted to plus delta t emitted, that is when it was emitted, and the time when it reaches here will be t observed plus delta t observed. This dt by at is also equal to r, right. The second crest has to follow exactly the same equation. So now we can equate these two. So let me equate these two and I can expand out this integral. So let me expand out the integral first. If I expand out the integral, what I have is t emitted plus delta t emitted to t emitted So this is what I get if I expand out the second integral. I have just taken the integral, the limits of the integral are still from t emitted plus delta t emitted to t observed plus delta t observed. I have written it up, broken it up into these three parts, and you can see that this part, this exactly cancels with this. So we are led to the relation that this integral should be equal to this. Now you see this interval delta t emitted is extremely small. So we can replace the integral by just delta t emitted by the value at emitted. We may assume that the function at does not change in this interval. Okay, similarly we may assume that the function at does not change in this interval. So we are led to the relation that this is equal to delta t observed by at observed. Okay, and since the time interval and the wavelength are exactly proportional, we see that the wavelengths satisfy this relation. So the wavelengths actually change because the time intervals change. Okay, so the wavelength of the light which is emitted is different from the wavelength of the light which is received. Okay, and this is occurring because, essentially because of the expansion of the universe. The first peak over here, the first crest, has to travel a smaller physical distance. A of t is an increasing function of time. So the physical distance that the first crest has to travel is less compared to the physical distance the second crest has to travel. So the time the first crest takes to cover this separation is less, the time that the second one takes is more. As a consequence, delta t observed is more than delta t emitted. Okay, and this implies that the ratio of the wavelengths also scales like this according to the scale factor. Okay, so essentially you can think of it as follows, that the wavelength gets stretched with the expansion of the universe because the ratio of the wavelength to the scale factor remains a constant. As the universe expands, if I have a wavelength, light of wavelength 1 meter, if the size of the universe becomes double, the wavelength also will become 2 meters. Okay, and then we can now calculate the redshift z. Remember that if I look at the ratio of the observed wavelength to the emitted wavelength, this ratio is what I call 1 plus the redshift. So light is emitted at a wavelength lambda emitted, it is received at a wavelength lambda observed, this I call 1 plus the redshift. Okay, and this here is then A emitted by A observed. Okay, the ratio of the scale factors. And if I assume that the observer is sitting at present, then we have that the 1 plus the redshift is, sorry, this should be A observed by A emitted, because they are proportional. So this is observed on top, emitted in the denominator. This is equal to 1 by A emitted, if I assume that the observer is sitting at present. Okay, in general it is the ratio of the scale factors. The observer is sitting at present, so let us assume that an observer at present sees light coming from a galaxy far away. The value of the scale factor we have assumed to be 1 at present, so I can put A naught equal to 1. 1 plus the redshift is essentially 1 by the scale factor when the light was emitted. Okay, so this now allows us to interpret the redshift straight away in terms of the scale factor of the universe when the light was emitted. So let me ask you a simple question. Suppose I observe a galaxy at a redshift 1. If I observe a galaxy at a redshift 1, I know then that the scale factor when the light was emitted, scale factor had a value which is, how much is it? It is half. The universe was half the present size. And suppose we also assume that the universe is matter dominated, completely matter dominated, then we know that the scale factor is proportional to t to the power 2/3. This is something very important that you should remember. If the universe is matter dominated, the scale factor is proportional to t to the power 2/3. Okay, so this is very important, because this gives a good approximation to the real universe for most of its evolution, except when it was radiation dominated in the past, but we don't see objects in that epoch. Okay, and if there is a cosmological constant, then it will be different in the future, maybe somewhere near the present, but most of the evolution it is like this. We can use it for most purposes, we can use it to make estimates. So if I know this, then I can ask you the question, what was the age of the universe, what was the age of the universe compared to the present age when the light was emitted? So what was the age of the universe? Please work out this problem, it is a very simple exercise. What was age of, how far back in the universe are we seeing when the light was emitted? So how far back in the universe are we seeing when we see a galaxy at a redshift 1? And you can determine this from the fact that the scale factor is proportional to t to the power 2/3. So we know the value of the scale factor now is 1, it is half at the time when the light was emitted. So determine the age of the universe, how far, determine the age of the universe at the instant when the light was emitted, or how far back in the time compared to the present epoch is the light coming from. Okay, right. So we have learnt how the redshift of a source, we have learned that due to the expansion of the universe, the light from distant sources, light from sources which we see from the past of the universe get redshifted, light from distant sources get redshifted. And the next thing that we would like to calculate is that we would like to, okay, before we go into any more calculations, let me now introduce something called the conformal time, which is very useful if we are studying the propagation of light in an expanding universe. So, the conformal time is introduced as follows. The same cosmological metric can also be written in the following way. So, let me introduce something called conformal time. So, I have not written out the length element in full. I have just represented this entire thing by dl square. It is essentially the length distance between 2 points. Okay. So, the same interval expression for the interval can also be written in this way, where we have introduced a conformal time d eta, which is dt by at. You see, all that we have done is that we have taken the factor a of t, which occurs over here, common outside. Okay. So, to do that I will get dt by a of t here. So, I have called that d eta the conformal time, and the line element now looks like this. Okay. This is called conformal time because this is very much like the metric in the absence of gravity, and the absence of gravity, that is correct, right, in the absence of expansion. And the expansion of the universe has gone in as a conformal factor outside. So, if I have an element, line element, and I multiply it with a function, this is called a conformal factor. Okay. So, that is the reason why this is called conformal time. Now, if you look at this, the advantage of this using the conformal time is as follows. Let me look at the propagation of light again in a space-time diagram. In my space-time diagram, if I plot r, and here if I plot c eta, then the light propagation of light is along 45-degree lines, because light will propagate along curves where ds is 0. So, d eta c d eta is equal to dl. I am looking at only the radial direction, so r will be equal to c eta. So, the light propagates along 45-degree lines in this space-time diagram. If you go back to the original cosmological metric, if I were to draw the space-time diagram in terms of t and r, the co-moving coordinate, light would not propagate along 45-degree lines because of this factor a of t here. Okay. So, the conformal time is very useful if you are looking at the propagation of light. The light covers equal co-moving distance in equal intervals of the conformal time. That is the important property. Okay. So, let me, time is nearly over, so let me bring today's lecture to an end over here. Let me recapitulate before that what we have learned today. We learned first how to interpret the cosmological space-time, which is represented through the cosmological line interval, or what is called a metric. This essentially allows us to calculate distances and intervals between events. That is the crux of the whole matter. And today we learned how to interpret it. We saw that you can, the space can be of 3 different kinds. It could be flat, or you are allowed the cosmological, the space, the cosmological, the universe that we live in could be spatially flat, or it could be a space of constant positive curvature or of constant negative curvature. We then took a closer look at what we mean by a space of constant positive curvature. It is a 3-dimensional sphere. And finally, I explained to you how to calculate the redshift of light from a distant source, how that is related to the scale factor, and we saw that the wavelength essentially scales with the expansion of the universe, which gives rise to the observed redshift of distant sources. Let me end today's lecture here.